Riemann-Hopf equations.
Good afternoon. All problems of turbulence mixing and beyond tied in some sense with the solution of hydrodynamic equation. Here I present the results which obtained with my son Artyom, and where we have obtained the exact solution of Euler-Helmholtz equation and Riemann-Helmholtz equation. The main result is that the exact solution of Euler-Helmholtz equation is coincide with the exact solution of vortex three-dimensional equation of Riemann-Hopf. Earlier Riemann-Hopf equation consider Zeldovich, Shandarin, but they consider only potential solutions. This, in this case, we have vertical solution, and because of this, the solution of three-dimensional Riemann-Hopf equation coincide with the solution of three-dimensional Euler-Helmholtz equation for compressible case when divergence of velocity is non-zero. For this solution, which obtained more than 25 years ago, but not widely known, firstly, the necessary sufficient condition of singularities are obtained, and it is possible to solve the Cauchy problem of turbulence, because it is possible to obtain the entropy and high moments of vorticity on the base of this solution. In this year, we make a remake of this paper, which is published in the Club of Russian of Academics of Science of Soviet Union in 1991. We used this exact solution to obtain a new analytical solution of NAVIER-Stokes equation, compressible NAVIER-Stokes equation, and thus we have the positive answer on the Millennium Prize problem, more exactly to the generalization of the Millennium Prize problem to the compressible Navier-Stokes equation, because originally the statement of this problem by Clay Institute of Mathematics was stated for divergence-free solution of Navier-Stokes equation, because for compressible Navier-Stokes equation assumes that there is no smooth solution of this equation on infinite time. Our solution have smooth on all time, on infinite time, and thus this on the basis of our results, we may say that assumption is not valid. Так, это что-то вырубил вообще все. Так. Так. Что ты нажал? Не то. Так. То есть я хотел листануть, оно... вот. Ну, давайте следующий слайд. Now I show how this is the Navier-Stokes equation for compressible case, and I show how we can reduce this equation to Riemann-Hopf equation. This is possible due to the this presentation of pressure, which is the result of the consideration of balance of integral entropy, and from the condition of positive rate of this integral. In this case, the Navier-Stokes equation reduced to this equation. This is Burger's type equation, three-dimensional or two-dimensional. If we take the operator rotor to this equation, we obtain the Euler-Helmholtz equation for the for compressible case when the divergence of velocity is not zero. This is the statement of CAUCHY problem for the case of compressible Navier-Stokes. This is the same as original CAUCHY problem for divergence-free case, but in this case we must consider the not only velocity but density also. This is the energy, this is the equation of balance of entropy, and you see the second member of this equation. This is which have possible to be negative or positive, and only in the case of the above condition on pressure, we have positive derivative of integral integral entropy when this member is zero. This is condition between the energy, the rate of dissipation of energy and integral energy and of entropy. For modeling viscous effect, we introduced the stochastic velocity, which have Gauss statistic and delta correlated in time, and thus we reduced the equation on Navier-Stokes to this Riemann type, Hopf-Riemann type equation. This is stochastic velocity. When we have averaged, we obtain the viscous term. The exact solution of this equation is have this form where this is matrix of this type depending only on the initial condition of velocity. In the one-dimensional case, this have this presentation, and the solution of this type obtained by Pelinovsky in 1976 and by me in 1989. And this is the case of arbitrary dimension, 2-dimensional, 3-dimensional. If we averaged this presentation of solution, we obtain this formula for average velocity, which have not singularity for arbitrary and infinite time. And thus we have the solution of compressible Navier-Stokes in this form. This is presentation of determinant of matrix, one-dimensional, which mentioned above, two-dimensional. This is dependence on time, and three-dimensional, where we have cubic dependence. If you consider the example when initial velocity field is divergence free, which have stream function of this type, the time of singularity when we do not consider viscous effect have this presentation which depend on parameters of initial stream function. And first, the singularity of solution begin on the ellipse. Describe this. This is presentation to vorticity field, which corresponding to this exact solution of Euler-Helmholtz equation in two-dimensional and in three-dimensional. This is presentation for helicity of this solution. This is presentation for entropy of this solution. You see that this is the case when we do not consider viscous effect, and you see that determinant stay in denominator, and when it's zero, it becomes infinity. And this is presentation for arbitrary moments of vorticity. This is the exact solution for this, and it may be possible to see from this that this value is more larger than the square of this value. It's corresponding to intermittency effects. But if we consider homogeneous friction, we may obtain also exact solution. But in this solution, we must replace the time on this ansatz. And for the case described by this formula, when homogeneous friction is larger than this value obtained from algebraic equations, which I presented before, we have a smooth solution at all times. This is important because in every numerical simulation of hydrodynamic equation, Navier-Stokes equation, we cannot consider infinitely number of harmonics, and introduction of homogeneous friction is analog of consider of finite number of modes, and thus we have condition which give us give for us a possibility to obtain smooth solution at all time without any instabilities which take place in numerical simulation. I have this is так, Chicago Newton difference. I've finished my presentation by showing the solution of two-dimensional equation, the example of which I demonstrate before when this is exact solution of two-dimensional vorticity equation. Thank you.
Thank you.
Once more, repeat.
There was a question. I think it's question 1.3.
Equation 1.3, yes. Yes.
Which are the coefficients in that equation?
This is condition which tied pressure with divergence of velocity.
Yeah.
In compressible case, we have zero divergence. And for this case, this is analogous of this condition, which corresponding to positive of rate of integral entropy. This is obtained from this condition.